All right, let's dive right into this explainer. Today, we're uncovering the invisible web of container networking, the absolute powerhouse behind modern apps. I mean, if you've ever wondered how the internet actually survives the absolute chaos of Black Friday, where companies like RetailNova handle, get this, 2.3 million requests per second without totally melting down, well, the answer is hiding in the microscopic architecture we're about to explore.
So here's our flight plan for today. We're going to hit the container illusion, namespaces, and control groups, networking the invisible web, the magic of internal DNS, and finally, scaling for Black Friday.
All right, part 1, the container illusion. We really need to start by shattering a huge misconception about where these apps actually live.
Think about it for a second. How do thousands of isolated apps talk to each other without crashing the whole system? It's a fascinating question, right? And it brings us face to face with this brilliant, lightweight illusion created by the Linux kernel. How do we literally have thousands of applications running on the exact same hardware, completely unaware of each other, but perfectly capable of communicating when they need to? The secret isn't faking hardware. It's about slicing up the operating system itself.
You see, traditional virtual machines are kind of like dragging around heavy luggage. They abstract the hardware to run a completely separate guest operating system. And man, that means a lot of overhead. But Docker? Docker takes a completely different route. It uses process-based isolation. It literally just shares the host OS kernel and isolates the app processes. It ditches the bulky nature of VMs. And that right there is exactly why containers boot up in seconds and need way fewer hardware resources.
Moving on to part 2, namespaces and control groups. Let's look at the hidden architecture inside Linux that actually pulls this illusion off. Think of namespaces like the translucent glass walls of a futuristic container. They independently isolate everything, processes, networks, files, so every single app just assumes it's flying solo. Take the PID or process ID namespace. From the host system's point of view, a container process might be, say, ID 1236, but inside its own little glass box, that container thinks it's PID 1, the very first process on the whole system. Then you've got the net namespace, giving it a private virtual network, and the mount namespace giving it a completely isolated file system. It is the perfect illusion of total isolation.
But here's the catch. While namespaces dictate what a container can see, C groups, or control groups, define what it can use. This is your ultimate safeguard against that one noisy neighbor trying to hog all the power. Imagine one malfunctioning container just trying to eat up all your CPU and memory. C groups immediately step in and say, nope, you're limited, throttling that resource usage to ensure fair play across all your running containers. So together, namespaces and C groups form the invisible scaffolding holding up modern infrastructure.
Which brings us to part 3, networking the invisible web. Because honestly, if these translucent containers are perfectly isolated, how do we actually get them to talk to each other?
Because an isolated app that can't hit a database isn't doing us much good, right? Well, Docker relies on 4 core network drivers to build an invisible, futuristic web of communication between these environments. First, you have the bridge driver. That's your standard for standalone containers to talk via IP. Then there's the host driver. This one totally removes network isolation, letting the app use the host machine's IP directly. Awesome for performance, but yeah, terrible for security. Then we have overlay. This is where the magic happens for distributed setups, allowing containers on totally different physical servers to talk to each other. And finally, none, which just disables networking entirely for maximum security. It is super cool to actually see these exact network drivers sitting right there in the command line interface, just waiting to route traffic. If you type docker network ls into your terminal, boom, there they are, bridge, host, and none. The big takeaway for us is how standardizing these networks completely replaces the absolute nightmare of manual IP configuration. You just attach a container to a network, and Docker handles all that messy underlying complexity for you.
But what about letting the outside world in? Well, Docker actually manipulates Linux IP tables to create network segmentation, mapping external requests straight through those glass walls we talked about. Since every container has its own virtual network interface, you could easily have 5 different web containers all listening on port 80 internally. No problem. Docker just maps those internal port 80s to entirely different distinct ports on your physical host machine. It routes the traffic perfectly, securely, and with 0 conflicts.
All right, part 4, magic of internal DNS. Because we still need to figure out how this data actually finds its moving target. When you've got hundreds of microservices spinning up and down constantly, relying on static IP addresses is basically a recipe for total disaster. So instead of chasing unpredictable shifting IPs, Docker lets containers simply call each other by static names, like DB or web. Think about it. A container dies, a new one spins up, and it gets a totally random private IP, usually somewhere in the 172.17 range. If you hard-coded that, your app breaks instantly. But by using user-defined bridge networks, Docker activates a built-in internal DNS.
It literally operates like an automated air traffic controller. It seamlessly translates that static name and routes a neon packet of light exactly where it needs to go. Let's trace it. Your web backend just says, hey, connect to the service named DB. Docker's internal DNS intercepts that request, figures out whatever dynamic IP DB happens to be using at that exact millisecond, and instantly routes the traffic. Your app's code? It doesn't even have to care about the network topology at all. It just works.
Which brings us to our final section, Part 5, Scaling for Black Friday. Because what happens when this perfect little microsystem gets hit by the macro scale of the real world?
How does this actually hold up when a company like RetailNova suddenly gets slammed with 2.3 million requests per second? Well, when those massive e-commerce surges hit, orchestration tools like Kubernetes swoop in to save the day. To handle that insane load, RetailNova's leveraged overlay networks to instantly spin up and connect thousands of new containers. And because they're already isolated by namespaces, throttled by cgroups, and instantly discoverable via internal DNS, an orchestrator can just copy and paste a web container thousands of times across dozens of servers, and the overlay network ensures they all communicate seamlessly.
And this isn't just one company. This reality is shared all across the industry. There's a great quote from Matt Law at the Warehouse Group. He noted that they started with about 600 virtual machines. They got that down to 400, but now they've got 3,500 containers. It perfectly captures why enterprises rely on this technology. Docker's reliable efficiency lets them transition away from that heavy hardware virtualization to a massive fleet of process-isolated containers. They are doing vastly more with the exact same server footprint.
Seriously, scaling to 3,500 interconnected containers is exactly how modern infrastructure chews through 2.3 million requests a second without a catastrophic crash. Can you imagine trying to manually manage the IP addresses, file dependencies, and resource limits for 3,500 applications? No way, it would be physically impossible. But when you trust this invisible web of user-defined networks and automated DNS, a system of that incredible size practically manages itself.
So, as we wrap up this explainer, it really leaves us with an inspiring thought about the limitless potential of this invisible web you now know how to build. You understand the underlying Linux namespaces, the resource-saving cgroups, and that super clever internal networking that makes containerization so incredibly powerful. The old infrastructure limits of the past, they are completely gone. If your app can scale from one single container to 1 million in a matter of seconds, are you still thinking too small? Definitely something to chew on. Thanks for learning with me.